Alright, so we're back. Turns out there was no food in the engineering office because you snooze, you lose. That's just it. We were all very disappointed and hungry. Sorry, I should have had a break earlier. Distance learning students didn't miss anything. Besides, I'm here to tell you the food there was lousy. The only thing I did was stand around and eat grapes. The other stuff I looked at kind of funny. It kind of looked like pork rinds that had been fried. I think they called them crinkles, or what do they call those things? Fried pork rinds. Is that anybody knows what that's? Pork rinds? There's a term for fried pork rinds, but it turned out it was really just dried fruit. But I looked at it kind of funny, like it was some sort of an animal that had better days. So I've got a couple of methods for altering an image. One is called direct methods and the other is called indirect methods. This is all within the homogeneous point processing area of image processing. Direct methods, like a lookup table, employ a mapping function. So that means you take a pixel value and you map it to a new pixel value. And so you can use that on the color planes for red, green, and blue. And so when we did the pseudocolor example earlier, we were using what's called a direct method of image processing. And when I created the invert filter in here, I just had one operation called invert, which took the red value and subtracted it from 255, its maximum value, to create what's called the invert value. And I did that for both red, green, and blue. Use the same function for both, and that we call homogeneous point processing, and it's an inversion. It inverts the image. Inverts it in terms of its appearance. So, for example, if you had the original image being displayed and then you wanted to colorize it, you could then proceed to make a new image, IMG, let's call it IMG3, and set it equal to imageutils.invert. Well, that's not working. Huh. Interesting, isn't it? I could have sworn there was a homogeneous point processor for inverting an image. I think there is. Let's go find it. It'll probably be under HPP filters. Ah, here it is, invert filter. Oh, it even has a main. Isn't that nice? That doesn't look like much. Invert filter. I guess what we can do here is make a new instance of the invert filter and then apply it. But let's see who else is using it. Negate. Oh, negate. Yeah, negate is invert. Okay, let's do that. Imageutils.negate. We'll try that. Imageutils.negate. Pass in the image, which the original image would be IMG, and then what we'll do is imageutils.display image, and we'll put in the negate image IMG3, and we'll give it a name, and the name will be negate spell it right, negate IMG, n paren sem. So let's see how that works. And then we'll do a little analysis. Here's an airplane. So here's the negate of the airplane. Here's the pseudocolor of the airplane. And here's the original airplane. So what we've done is we've taken the red value and subtracted it from 255 to create a new value. And we're calling that the negate of the image. Remember, values have to range between 0 and 255, so you can't have minus 255, but what you can have is the value minus 255 and then add 255 back. That doesn't make sense, so why not take the value and subtract it from 255 and call that the negate? And that's the only thing that seems to be consistent with the notion of what negate means. So then if you take a look at how that's implemented, here's the invert processor, and then I just do something called process the image, which apparently takes an image processor interface and then applies it to each pixel in the image. So let's first look at the invert filter, and it uses something that says it's the value minus 255, and then it does clipping. If it's less than 0, make it 0. If it's greater than 255, make it 255, because those are the ranges, right? That clipping means you can't go below 0, you can't go above 255 because you're dealing with an 8-bit quantity. So that's fair. And we'll use that for both red, green, and blue. And we'll call that an invert filter. Implements the homogeneous point processor interface. So is that clear? I'm not hearing a yes. It's okay?
So it just gives you back red,
green. Yeah, the homogeneous point processor interface requires that I implement get red, get green, get blue. Then it doesn't tell me how to implement it. That's the polymorphic part of it. So now with the invert filter, I implement red, green, and blue functions with an invert function, and I apply the invert function uniformly to both red, green, and blue. So then the way in which the invert filter gets used, that's the interesting thing. The negate, which takes an image in and returns an image, takes the invert filter and implements something called process. And so it processes the whole image with the invert filter. Let's see if I can get back there. Here it is. So what does this get processor do? What it does is it says, okay, I've got a processor which takes the invert filter coming in, and it passes it to a thing called the image filter image, the HPP, the homogeneous point process filter image processor. That's circuitous. And what it does is it takes that interface implementor, comes up with the lookup table, and then proceeds to apply the interface implementation to construct the lookup table. This is a very efficient, hacky way to go about doing image processing, but it works really fast. And then when somebody calls getImage, it applies the filter to the image. Now the question then becomes, how does this bio.filter work? This is part of the AWT. So where does bio come from? Buffered image operator. So what this is doing is it's creating an image, it's creating a lookup table. From that lookup table, it makes what's called a buffered image operator. The buffered image operator is part of the abstract window toolkit, and the abstract window toolkit allows me to take buffered image operators and apply them to images very fast. So once the buffered image operator is created, and this is a bit hacky, I know, but it's one of those things where, it's part of what we would call Java advanced imaging. you're kind of given all the code, and now what you're doing is you're taking this sports car and you're looking under the hood and you're saying, oh, that's how the engine works. And you're like, okay, I can still drive the car without actually knowing how to tune up the Porsche engine, but in case I want to know how the engine works, I give you everything. The buffered image operator is a part of the Java Advanced Imaging API. And so by creating a lookup operation using a lookup table, I can do very fast image processing. So what can I say? It's an image processing hack, and it works really fast. And that's one of the reasons why I decided to embrace it. Do you need a buffered image operator to do this kind of image processing? And the answer is no. You could have done it without it, and it would work fine. It would just be a little slower. So I kind of was trying to trade off speed and kind of make it a little easier for people by creating the image processor interface and maybe the homogeneous point processor filter. Does it make it easier? I don't know. I still don't know. Design of systems like this is tough. It's never clear what the easiest way is to do these kinds of designs. But it was clear that the buffered image operator was supplied to me by the Java Advanced Imaging Toolkit, and I figured why not use it. So that's the way it went, for whatever reason. At the end of the day, my way of approaching this was, look, I'll give you the homogeneous point processor filter interface. You implement it, and now I've got ways in which to make that very fast and make buffered image operators out of it. And those operators will run as fast as any Java app that Sun would produce, or Oracle nowadays. So here's how the invert works. Inversion is not the way you would normally think about inversion, right? We went to the maximum value for the dynamic range, 255, and we used that as something that we would subtract from. We call that inversion. It's almost like a one's complement inversion. So we talked a little bit about the direct methods. The direct methods use a mapping function, like a lookup table. And we can apply those mapping functions to the color plane, which is kind of what the lookup table does, right? And we could see the different colors coming out, and that's fine. There's something else you can do, and this is I would call this the stochastic view of image processing. And with the stochastic view of image processing, what you're really doing is you're creating a population profile for pixels. That just sounds cool, right? The population profile for pixels. Just the alliteration just sort of smooths out there. Population profile for pixels. You could say that 10 times fast. Population profile for pixels. So anyways, if you had, let's assume you had a class filled with students, right? And this class of students had, let's say there was 10 students. And half the class got an A. So 5 students got an A. And the other half of the class got a C. 5 students got a C. So then you say, what is the probability mass function for the class? Well, it would say for value A, you'd have 50%. For value C, you had 50%. Right? That's the probability mass function. Now let's assume the distribution is somewhat different. Let's say 2 students got an A, 2 students got a B, 2 students got a C, 2 students got a D. Let's see. A, B, C, D. That's 8 students. 2 students got an F. That's everybody, right? So now you'd say the probability mass function for the A is 2 out of 10, which would be like a fifth, and maybe a fifth would have like a B, and a fifth would have a C, and a fifth would be like a D, and a fifth would be like an F. Right? That's called probability mass function. Now, why is that different from a probability distribution function? How come that's not a probability distribution function? Why is that? Say it again? You forget. Yes, sir.
Oh, no, I
You forget. Kyle, do you forget? Kyle forgets. Kevin, do you forget? He forgets. Arodi, you forget? Thanks, Arodi. How about Rich? You forgot. So the reason we're all forgetting is because there's really no difference between a cumulative distribution function and a cumulative mass function, or a probability distribution and a probability mass function, except for one thing. And the difference is one is discrete and the other is continuous. So with a continuous random variable, you get a probability distribution function. When you integrate the random variable over a period of whatever, time, or whatever it is you're sampling, then you get a cumulative distribution function. That's because it's an integral. But if you're dealing with discrete things, like a discrete number of students, then you have a probability mass function. And so what that means is when you want to compute the cumulative mass function of all the students that got below a C, you have to add up the probability mass function for those that got the F, for those that got the D, and for those that got the C. And so if 1/5 got a F, and 1/5 got a D, and 1/5 got a C, then 3/5 got below a C. That's a cumulative mass function. And the reason they got below a C is because they couldn't remember the difference between a cumulative mass function and cumulative distribution function. So now you remember, right? And you can do the same thing for pixels. For pixels, what you do is you look at the different values and you figure out how many pixels got that value out of the total number of pixels. They call that sample statistics. With sample statistics, you use what's called historical empirical measurement in order to be able to determine the statistical profile of the random variable. And so what you do is you look at the pixels and their values and you say, aha, and according to this slide, 0 is a value for a pixel. It occurred in 32 out of 64 pixels. Therefore, half the time, you got a 0 value. That's a probability mass function. 128 happens 16 pixels out of 64. So you can get a probability mass function for that. If you wanted to determine what the cumulative mass function would be of all the pixels above 128, that is 128 or above, what would you get based on the table that you see here? I'm doing the cumulative mass function of all the pixels whose value is 128 or above. Yeah, 0.5, sure. 0.5, perfect. Or 32 out of 64. So you just added them. And in fact, when you do the cumulative mass function continuously computed from value 0, all the probabilities will sum up to 1. And that's very satisfying because we expect all the probabilities to sum up to 1. That works out really good, especially if we have 100% certainty on what the probabilities are. And in the case of doing a direct measurement of the pixels values, we do have 100% certainty. Which begs the question, what happens when you don't have 100% certainty on the probability? There's a theory, right, which you guys probably never heard of, called the Dempster-Shafer theory of evidence, which allows you to create a math which is faced with probability that has uncertainty behind it. Because a lot of times, here in the real world, probabilities are not known with 100% certainty. In the area of poker, they might be known. In the area of maybe historic review of random variables, like in an image, they might be known. But if you're thinking about something that occurs in the future which doesn't have any direct measurement or bearing on what may happen in the past, like the stock market, probabilities are not known with 100% certainty.
They use that theory in failure analysis and stuff like that.
I'm not sure who they are. I know that it could be done. The Dempster-Shafer theory of evidence is fairly well known and has been for decades. So it's possible. It's not typical.
It's not popular.
It's not popular. It's not popular. It's tough. I mean, it's interesting, but it's not what we'll be able to do in this course, unfortunately. So when I think about discrete probability distribution functions, I think probability mass function. When I think about discrete cumulative distribution function, I think about cumulative mass function. One is continuous, the other is discrete. When I think about tossing a coin, I'm in the discrete space because the random variable has an outcome which is either heads or tails. Every experiment has two outcomes. That makes it have a binomial distribution function, or if it's discrete, binomial mass function. Temperature, that's a continuous variable, right? Time, that's a continuous variable. Space is a continuous variable. If I want to do a cumulative mass function and do the computation, I do a for loop and do a summation. If I'm doing this with a cumulative distribution function, it's time for integration. So it's the difference between a summation and an integral. Mathematically, very similar. And so here we go. Let's do a computation for a cumulative mass function. And what we're going to do is we're going to go through each variable, in each pixel in the plane of x and y, or I and j in this case, and we're going to mask it with a number 0 ff, which is 255. And then what we're going to do, and after we isolate the least significant 8 bits, is we're going to use those 8 bits as an index into an array. And then we're going to increment the value of that array. And so, since the array is going to range between 0 and 255, we're going to make sure that the values never generate an array out of bounds exception at runtime, because the values, by being masked with 0xff, will always range between 0 and 255. And then when we hit a value inside the histogram array, we'll increment that array element. It says, aha, I found a variable whose value is 128. Let's increment the 128th element. Then I found a value that's 129. We'll increment the 129th element. So we'll keep a total count of the total number of pixels. And once we do that, after we have the total number of pixels, we go through and normalize the histogram array, and that'll give us the probability mass function for the image. And that's how you do the computation efficiently. Now you could say to me, but Professor Lyon, most images are not black and white. They're not grayscale, and they don't just have values from 0 to 255. They have 16 million different colors. And that means you need to have a histogram array that's 16 million different elements long. Yes, that's a very astute observation, and I'm glad you made that observation. And having an array that's 16 million elements long will almost certainly cause you to run out of memory in the heap for the Java virtual machine, despite the fact that you have gigabytes of memory sitting in your laptops. Therefore, You will not be able to do that. You'll have to do a histogram array that's separate for red, and then another one for green, and another one for blue. You could say, but Professor Lyon, that histogram's not a real histogram. You really ought to have a full-blown histogram with 16 million different elements. And I could say, yes, you're absolutely right. We should have that. But we don't. Because here in the real world, we're trading off space for time, and we just don't have the space. Right? And it would take no more time to index into a 16 million element array and just increment it whenever it comes across that value. It really wouldn't. Unless the array were stored in virtual memory that had been swapped out onto the disk. But making an array that's 16 million elements long, I don't think Java likes that. I think Java gets real cranky if you do that. How do you make Java cranky? Here, let me show you something. We'll make Java really cranky. Let's make an example. Here's a new example. Let's call it Cranky Java. Cranky Java. And what we'll do here in Cranky Java, Cranky Town, is we'll make a main, and we'll create an array. Let's think about this. How about an array of int? Integer array equals new int of 1 to the 16. So we'll shift over to the right. No, we need 24, right? 24. And then we'll initialize it for integer I equals 0, while I is less than ia.length, I++, and then we'll just say ia of I equals I. Right? What could possibly go wrong? I mean, the compiler likes it. There's no syntax errors. It looks fine to me. I'm feeling an exception coming on. Oh, he likes it. Oh, gee. Here's a new way to do a histogram. I'm liking this. So I can now do a histogram by reading in all the pixels from an image and then taking those pixels as 24-bit quantities and piping them into the histogram array here, IA. I don't know why this worked. This never used to work. No kidding. Usually it would blow the heap away. But it seems to be okay with it. Yeah, I thought Java would be cranky. Print utils. I know this is going to take a while, but I just figured what the hey. And Alt-Enter. And does this actually work? Oh, wow. Look at that. Too much to process. Too much output to process. That's fine. Wow. Disconnect. So you can... Yeah, I don't think I can do that. So, how would you make a histogram with real 24-bit quantities using an image? Well, first thing I think you'd need to do is get yourself an image, right? Utils dot get image. Get image. Right? Alt-Enter. Alt-Enter. Okay, he's happy with that. Now, how would you get all the pixels off of that image as a single one-dimensional array? Could you do that? Image utils dot get pixels. Oh yeah, here they are. And put the image in. Ta-da! And what does that buy me? Pixels. Integer pals. That's an array. So that's all the pals in the image. But think about it now. Int is a 32-bit quantity. And we only allocated 24 bits over here. I guess we have to crank it, right? 32 bits. How big is 2 to the 32? That's a BAN for big ass number. That is a humongous number. So that's, shall we call that gigabytes? I think we don't have that many gigabytes available to our Java virtual machine. This is going to make Java cranky. I'm here to tell you, Java will be cranky on this one. Let's give it the baboon and watch cranky Java. Well, it's certainly cranking. The output can't be 0. "32 bits. That's big time. 32, 2 to the 32. It likes it. How could it return 0? The shift operation left shift by overly large constant value, more. What is this? Control F1? He's liking this? Shift operation by overly large constant value. Report shift operation where shift value is constant outside the reasonable range. Integer shift operations outside of range 0 to 31 and long operations outside of are reported. Shifting by negative or overly large values is almost certainly a coding error. Yeah, that makes sense. Why don't you try that? You like that? There you go. Negative array size. Why? What's the most significant bit in a scalar quantity? Sign bit. So what did I do? I just set the sign bit to -1, and so what this means is I've got a very large negative number, and negative numbers are not permitted for array indices. So what do I do? Well, I'm thinking 24 bits is plenty, and what we'll do is we'll go in and we'll grab the integers and we'll strip out the alpha plane. And we'll strip out the alpha plane by indexing into pels of I, and ANDing it with 0x FFFFFF, and then we'll just grab the least significant 24 bits. Does that make sense? The least significant 24 bits, or least significant 3 bytes, will be ANDed with pels, and then we'll use that as the index into our 24-bit histogram. Right? This is a sweet bit of code, and then we'll increment the element at that location ++. I don't really like clever code, but I've been known to write it from time to time. I'm not proud of it. What I've just done is I've used the value of the pixel, which is a 24-bit color quantity. I use that to index into the array, which is counting how many times that color occurred, and then I increment it every time the color occurs, and I call that a direct color 24-bit histogram, which isn't supposed to work, but is working for some reason I cannot explain. Maybe it's because they updated to IntelliJ 13 and now I have a great big heap. So now when I print this, what I'm really printing is a histogram. It's a giant, humongous histogram. It's something I can't visualize, and it's not something I'm normally visualizing. I wonder if I can print line with it. Yeah, works good. All right. Does that work? I'm surprised Java isn't a little more cranky. Array index out of bounds 65,536. Let me think about this a minute. 65,536 is 2 to the 16. Why would it stop at 2 to the 16? Two to the 24, that's a rather larger number than 2 to the 16. Right? 2 to the 24 is like 16 million. And 2 to the 16 is 65,536. And 16 million is bigger than 65,536. By like a lot, right? So what's up with that? I'm totally confused by this. SOUT, Control J, Enter. Let's just write out some little debugging thing. The length of IA is equal to end quote plus IA dot length. Right? That should be like bigger than 65,536. So maybe Java is cranky after all. We'll start off with some clouds, and we'll hit open. Now look at the length of IA. That really is 16 million. But then look at the error. Array index out of bounds, 262,000. Well, what's up with that?
That's 2 to the 18.
He's pretty unhappy with an array that's supposed to be like big. Right? There's 16 million. Here's a number that's somewhat less than 16 million by like a lot. I feel Java has gotten very cranky. And yet something here is going on that's preventing IA from incrementing properly. Now what you could do is guard the input. You can refactor this code by introducing a variable. If I can control the pop-up. Introduce inline. Let's see. There should be something called introduce variable. You don't see that here, do you? Oh, extract variable. Enter. So now if IA is greater than, let's see, if IL is less than IA.length, then we'll do the increment. So that guards the input. I think that might be I1. The 1s and the L's look very similar here. So it shouldn't go off the edge of the array, in theory. So here's Dr. DeFracto again, and he's unhappy because he couldn't go beyond 76,800, whereas the array length was 16 million. Java is cranky. No doubt about it. And so that's why you can't do a direct color. Yeah. So this is good documentation, actually. Here is why you cannot do a direct color histogram in Java using a 16 mega word array. Right? Because Java is just, he's just totally unhappy with the idea that you have 16 million elements in an int. He just doesn't want to deal with it. Now that's not part of the Java language specification. That's an implementation issue. And we can't blame the spec for that, but it's the reality of the language. Is everybody sort of understanding what I'm trying to do here? Does it make sense? This is direct measurement of an input image. We're trying to count how many pixels are of each value. We took the values and we made sure that those values did not exceed the total length of the array before we set them. But it didn't matter because those array elements weren't there, and we got an array out of bounds exception at runtime. Well, the same thing is going on here, only with a much smaller array. Here we all have 3 arrays, red, green, and blue. Each one goes from 0 to 255. And we'll use a screen, a mask, that goes 0xFF to make sure the values that come in are from 0 to 255. Then when we're done, and we've done the probability mass function computations, it'll be because we've taken the histogram array counts and we divided through by the total number of events. Each event will be corresponding to another pixel that occurs. So if you've got 1,000,000 pixels and you found half of them were under, I don't know, were a value 0, then you would say, aha, the histogram array at value 0 is equal to 50%. I think we're out of time. How are you guys doing with the reading? Alright, what I'd like you to do is continue with your reading in Chapter 4. You should be able to read about histograms at this point. I'm not going to assign any homework other than the reading. And have a good evening, and drive safe, drive often. Good evening.